Not quite sure. I restarted. YouTube says I'm streaming. I think I might have screwed it up by. You were met with a transistor? Yeah, that sounds right. That sounds right. Hmm. Okay, well, Twitch just might have to be what I support at the moment because it looks like the YouTube got out of sync. Sometimes that happens when you hit the multi-stream, it will put the YouTube, like if you stop one YouTube begins the live stream, your Streamlabs will be using a different key than if you hit start from YouTube. And I think I did that, so I'll have to fix that later, but Twitch will be it for now for the rest of the stream. I was honestly just looking at syntax though, nothing too crazy. Looking at the string from, because we have, I guess, a few different ways. We were looking at ownerships. That's what it was. Ownership. If you use the string library, you get to actually use some of these other things, which is cool. Such as push string, which appends a literal to the string. Okay. That's handy. In case of a string literal, we know the contents of compile time, so the text is hard-coded directly into the final executable. This is why string literals are fast and efficient, but these properties only come from a string literal's immutability. Fortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. With the string type, in order to support a mutable growable piece of text, we need to allocate an amount of memory in the heap unknown at compile time to hold the contents. This means the memory must be requested from the memory allocator at runtime, and we need a way of returning this memory to the allocator when we're done with our string. So, okay. So you use it once or use it however many, okay, and then you free up the memory again. It's part of the collection kind of garbage collector, yeah. Okay. Garbage collector keeps track of and cleans up memory that isn't being used anymore. We don't need to think about it. In most languages without a garbage collector, it's our responsibility to identify when memory is no longer being used. And to call code to especially, yeah, to free it. Right, we had to do that in C. That makes sense. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. Yes, that is a problem. So we pair exactly one allocate with every one free. Yep. Rust takes a different approach. Memory is automatically returned once the variable that owns it goes out of scope. Oh, okay. Why is this a weird concept? This seems pretty straightforward. You simply, oh, it's working? It just worked on its own? Okay, all right, YouTube's working now. I'm glad it figured it itself out. Anyways, this seems like a straightforward concept. If you do allocating memory, then it will be freed on its own. How is that different? Oh, I guess the difference is you don't call it yourself, so the garbage collecting is the would be the act of you calling that function. Is that what they're saying? All right, there's a natural point at which we can return the memory our string needs to the allocator when S goes out of scope. When a variable goes out of scope, Rust calls a special function for us. The function is called drop. It's where the author of string can put the code to return the memory. The rest calls drop automatically at the closing curly bracket. I haven't used this, so that note doesn't pertain to me. This pattern has a profound impact. Yeah, I'm sure. It may seem simple right now, but the behavior of the code can be unexpected in more complicated situations when we have multiple variables use the data we allocated to the heap. Okay, thank you. I figured that was a naive thing for me to say. That would be straightforward. Multiple variables can interact with the same data in different ways. Let's look at this. So we're saying let x equal 5. X is immutable and it's equal to 5. So if you were to say let y equal x, that should take 5 and put it into y. You can probably guess what it's doing. Bind the value of 5 to x, then make a copy of the variable in x and bind it to y. We now have two variables, x and y, both equal to 5. This is indeed what's happening because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. But if we do string, where we're allocating an amount, where we say put hello on the stack at S1, and then say S1's, what does it say, bind the value to S1 to S2? I wonder what would happen. This looks very similar, so we might assume that this way would work the same, but, oh wait, they don't say but. That is, the second line would make a copy, but this isn't quite what happens. Okay. Ooh, we got a figure. Nice. String is made up of 3 parts, shown on the left, a pointer to the memory that holds the contents of the right, a length and a capacity. String, length, capacity. So that's multiple data. Oh, I see. And then what we got? Oh, this is the pointer to the actual string. Yeah, this makes sense. This group of data is stored on the stack. On the right is the memory on the heap that holds the contents. Oh, wait. So S1's on the stack, but this is on the heap? Is that how it's going? Okay, the group of data stored on the stack. Yeah, wow. So this metadata from string's actually a, what would you call that? A class or a struct? It's more like a struct to me. They might call it a class. It's like a struct pointing off to your heap memory. So this is your stack on the left and your heap on your right, or at least contents that would be in each. That's interesting. Okay. The length is how much memory in bytes. Oh yeah, this is just explaining what these are. Yeah, I know what length is. I know what, wait, what is capacity? Capacity is how many bytes in of memory. Wait, okay, let me actually read this. Maybe I'm not quite getting this. Length is how much memory in bytes the contents of string being this data type, are currently using. So this is using 5 bytes. Meanwhile, the capacity is a total amount of memory that string has received from the allocator. Oh, okay. Capacity correlates to how long this is, but 5 correlates to how much of the allocated space it's currently using. Okay, I see. So you could allocate for more, but not necessarily be using all of it. That's interesting. So when we assign S1 to S2, the string data is copied, meaning we copied the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. I see. So theoretically, if you were to exit scope with S1, but somehow S2 is in a different scope, S1 would deallocate hello, so S2 would not see hello. That is my prediction, at least. The representation would look like, wait, hold on. Figure 4.4-2. The representation does not look like 4-3. Oh, yeah. Yeah, no, it looked like 4-2 because it's pointing to the same address in memory. Yeah, this is just like pointer theory. That makes sense. We said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up. Figure 4.2 shows both data pointers pointing the same location. This is a problem when S2 and S1 go out of scope. They both try to free the same memory. This is known as a double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, after the line let S2 equal S1, Rust considers S1 as no longer valid. Really? So then what? So if you did S1 here, it's just ignored? Therefore, Rust does not need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. It just, yeah, compile error. And then they give you an alternative solution. Although I don't think that's really a solution. They tell you what the problem is, though. Value borrowed here after move. Yeah, that makes sense. If you heard the terms shallow copy and deep copy while working with other language, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shadow copy. But because Rust also invalidates the first variable, instead of being called a shadow copy, it's known as a move. So an example, we say S1 moved into S2. Basically, since S1 got erased, yeah, basically S2 is now the owner of the data that S1 originally was the owner of, because there can only be one owner. I now see where this is going. Okay, with only S2 valid, when it goes out of scope, it alone will free the memory and we're done. In addition, there's a design choice that's implemented by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Okay. I'm not actually seeing what. So it said it wouldn't compile up here. So they're saying you just shouldn't do that? Or it's saying they solve it automatically? Okay. I guess I should keep looking. Yeah. If we do want to deeply copy the heat data of string, not just the stack data, we can use the common method called clone. So make a clone to S2. Okay. So if you did do S1, I'm thinking they just said that it automatically goes away. The language, or maybe not. Maybe not. But this looks like the solution. This clone function is the solution. If you wanted this behavior at least. When you see a call to clone, yeah, you know some arbitrary code is being executed and that code may be expensive. It's a visual indicator that something different is going on. This works just fine and explicitly produces the behavior shown in figure 4.3. 4.3 is this one. Okay, got it. Stack only data copy. So So there's another wrinkle we haven't talked about. This code uses integers, part of which was shown in listing 4.2, works and is valid. So 5 goes to x. X is copied over to y. This code seems to contradict what we just learned. Yeah, I agree. But it's because you don't have to deal with the heap, so it doesn't matter. X is still valid and wasn't moved into y. The reason is that types such as integers that have known size and compile time are stored entirely on the stack, so copies of the actual values are quick to make. That means there's no reason we want to prevent x from being valid, so we create the variable y. So calling clone wouldn't do anything different from the usual shallow copying. We'll leave it out. So clone is deep copying. Is that what they said? If you want to do deeply copy, then we call clone. Okay. It assumes shallow whenever it can. A special annotation called the copy trait that we can place on types that are stored on the stack as integers are. If a type implements the copy trait, variables that use it do not move, but rather are trivially copied, making them still valid after assignment to another variable. Rust won't let us annotate a type with copy if the type or any parts of it has implemented the drop trait. If the type needs something special to happen when the value goes out of scope, and add the copy annotation to the type, we'll get a compile time error. We need something special. You can trigger that? So when this thing would normally do drop, you can trigger it to, we add the copy annotation to that type. We'll get compile time error to learn about how to add. Okay. Let's annotate a type if the typer has implemented the drop trait. Does that mean like certain data types have these different traits? Is that what I'm getting? Huh. This is different, as they warned me. So what types implement the copy trait? Group of similar scalar values can implement copy, and nothing that requires allocation or in some form resource can implement copy. The things that are similar, all integer types, Boolean, floats, character, tuples, if they are all the same, I'm guessing. If they only contain copy types. Yeah, these are, string is heap, so that makes sense. Or maybe because they're different. Mechanisms of passing a value to function are similar to those when assigning a value. Listing 4.3 has an example. Okay. Where the variables go into and out of scope. So we have our main. We have a string, which is trying to put hello on the heap. It's giving it to S. S is taking ownership. This is a function called take ownership. So S is passed into here. But the thing is, when you take this, it's putting it on the stack. Moves into the function. It's no longer valid here. Yeah, that's exactly what I was thinking. Okay. So this is no longer in the same scope as this. So you're deallocating what this is as soon as you pass it into this function because it's in a different scope. Interesting. They're saying you pass in the name of some string and then this is the data type. Some string was the variable name and you want to put in this brackets. It goes out of scope and drop is called. The backing memory is freed. Okay, so we come back. We let x to 5. 5 goes to x. Makes copy. 5 goes into here. X would move into the function, but I32 is copy, so it's okay to still use x afterwards. Oh, okay, I got this backwards. What happens is S is passed into here. That's fine. But as soon as, S with the value hello comes into here, hello comes into here, hello is actually printed, but you get to the end of this function, which automatically calls the drop trait, which means you now come back here and S is empty because it's been deallocated. So this would print what you want. This would print hello, and this would print 5. It's just you could now make 5 here. You could use 5 afterwards, as it says. Wow, that's kind of crazy. Yeah, that's... Huh. But basically, the moment you leave any kind of scope is when things go awry. Maybe not awry, but just clear out. That's new to me. Oh, this would this would throw a compile time error. Well, okay, if you try to use S. If you didn't, then nothing would happen. Okay. Try adding code domain to see. They use S and X to see where you can use them and where the ownership rules prevent you from doing so. Okay. Where are we at? We're at the bottom of this page, almost done. Returning values can transfer ownership. So that would make sense because you want the ownership to go to whatever's receiving it. You're done with using whatever the function produced. You want to give it away. You want to give it to the output. So the ownership goes to S1. You have S1. Your string goes to S2. You're passing S2 into 3. Oh, hold on. This is where things going weird. This would get deallocated is what I would think would happen. So you pass S2 into here, which calls, takes and gives back. So this function, it returns a string. It takes a string. This is saying, let's return the passed in string because there's no semicolon. So it's returned. It doesn't actually drop it. That's kind of crazy. What the heck? Not as straightforward as I thought at all. So this returns and goes S3. As the comment says, S2 is moved into, takes and gives back, which also moves it to the return value for S3. S3 goes out of the scope and is dropped. S2 is moved, so nothing happens. S1 goes out of the scope and is dropped. Right. Makes sense. I didn't even see this gives ownership call. That's funny. Give ownership, you call it, it returns a string. Oh, I see. So if you have yours, you pass it to some string, it returns some string. So based off of what we just learned, yours actually goes into S1. S1 would have yours. And that's what they're saying here is it's S3 is dropped, S2 is moved, S1 is dropped. Huh. Wild. Ownership of the variable follows the same pattern every time. Assigning a value to another value moves it. Or sorry, assigning a value to another variable moves it. When a variable that includes data on the heap goes out of the scope, the value will be cleaned up by drop unless ownership of the data has been moved to another variable. While this works, taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again. In addition to any data resulting from the body of the function that we might want to return as well. Rust does let us return multiple variables using a tuple. Okay. Hello gets put in S1. S1 gets passed into function calculate lengths. Calculate lengths returns a string and a unsigned in a tuple. Use size would be the size of value. All right, so S, you're getting the length of S, which is put into the length Well, hold on. It's moved into the length value? Oh, just length though, not the whole thing. So length gets set into this, and then you return a tuple called S and length. So you're separating out the length, which is what this function is. You're calculating the length. Okay. So then you store S into S2 and length into len. You're moving S2 into that, but len, I would imagine, would be its own thing. The length is this. Yeah, this function would, I would say, would pass. But this is too much shimmering and a lot of work for a concept that should be more common. Luckily for us, Rust has a feature for using a value without transferring ownership called references. Hallelujah. This pass by reference, pass by value, perchance? References and borrowing. Okay. The issue with the tuple code is that we have to return string. We can use string after to call the function. Yeah, this is getting to the really deep-rooted stuff of Rust, I would agree. Otherwise known as fun. Okay. Where are we at? So string after the call. Yeah, okay. So yeah, string, pass it to here, you calculate the lengths. Okay, we're back here. Yeah, this is the function. So they're saying, here's how you would define and use length that has a reference to an object as a parameter instead of taking ownership of the variable. Oh, the ampersand. You're passing a reference. It's just like C. You're passing a reference to it, but if you don't pass a reference to it, it's a little bit wacky, I would definitely say. If you're passing the value, it's way more wacky. First, notice that all the tuple code in the variable declaration and function return value is gone. Okay, well, let's just look at this. So it's S. S is what you would pass into this function, and it's just a pointer. You're passing nothing else. You're just passing the pointer. S1 was the pointer. Oh, wait, sorry. S1 was the pointer that had hello and everything else, which this is what S1 is. So you're pointing to this, which happens to have the pointer to hello. And the return value apparently is gone when you run that. Pass the reference of S1 and calculate length and its definition. We take the reference of string rather than string. Yep, this is just how you're calling it. That's what they're saying. Okay, the opposite of referencing is dereferencing, which is accomplished as a dereference. Okay, so it's like C. That's good. Okay, ampersand S1 reference to the value of S1, but does not own it because it does not own it. The value it points to will not be dropped when the reference stops being used. Okay. Okay. So this protects this from being dropped. All right, reference seems way more valuable. Yeah, I mean, if you still want to keep that, you can just pass this in, use it a little bit, and then this wouldn't change. If you did want it to clean it out, then that's fine too, I guess. But I feel like I'd use this implementation way more. I'd have to see some examples, but that's what I'm thinking. Yeah. Ampersand string. This is only relevant if you're doing heap stuff. I mean, ideally in low level, you never use the heap. So I wonder how often this will come across my programming adventures, but still, I was curious how they handled pointers and stuff. Okay. All right, so they're saying let's just create a reference. Oh yeah, we already read that, I think. Uses this to indicate the type of parameter. S is a reference. Yeah, that's just talking about the syntax. Okay, the scope in which the variable s is valid is the same as the function's parameter scope, but the value pointed to it by reference is not dropped when s drops. Yeah, okay, that's what we said. That's fine. Recall action, borrowing. This is borrowing. As in real life, if a person owns something, you can borrow it from them. That's fun. They're really getting into the analogies here. This is borrowing S1's contents. S is borrowing S1's values. Cool. All right. So what happens if we try to modify something we're borrowing? Spoiler alert, it doesn't work. All right, let's see what their function is. You pass an S as a reference so that way it can be borrowed. You want to append a world to that string you're borrowing, but it works more like a read-only. You can't actually change this. This is a read-only. So if you do this, you get a compilation error. Just as variables are immutable by default, so are references. We cannot allow to modify something we have a reference to. I see. So then you say, okay, we can let you change it a little bit. You're going to borrow it, but we can let you write on it. We can let you draw on it, whatever, because it's mutable. You pass immutable, then they can append world to it. And when it comes back out, S has now a value of comma world. Does that mean it grows the length and capacity of the string since it's built into the... I'm guessing this function would do that automatically. Okay, I'm just seeing if they say anything different than what I just said. I don't think so. One big restriction. If you have a mutable reference to value, you can have no other references to that value. This code attempts to do that. Okay. S. Mutable reference to R1 or at R1, R2, also mutable reference. I see. I see why they wouldn't want this, because if you're changing it at 1, you're changing it at 2, how do you know which one writes what first and second? Even though it should be like, left to right, who knows? It's kind of an unsafe situation to be in. And that's what this thing's all about, security. Okay. The first mutable borrow is in R1 and must last until it's used in the println. Yeah, when does it get freed? How does it know to be freed then? But between the creation of mutable reference, it gets tied to R2. This restriction, preventing multiple mutable references to the same data at the same time, allows for mutation, but in a very controlled fashion. It's something the new Rust creations, or Rustations, there we go. It's about security, but there are times you need unsafe with the unsafe keywords so you can have controlled chaos. Yeah, I saw that a little bit. Unsafe is a fun little keyword. It's funny that they can call out like, okay, everybody, this is unsafe code, but I know what I'm doing. That's pretty fun. All right, the benefit of having this restriction is that Rust can prevent data races at compile time. Data race, oh yeah, this is exactly what I'm talking about. The erase conditions, they're calling it data race. Okay. 2 or more Calendars access the data at the same time. Yep. At least one of the pointers being used to write. The other one, no mechanism to synchronize. Yeah, that's just a race condition. Yeah, makes sense. They're just saying it's a bad thing to have, of course. You can use curly braces to create a new scope. So you literally force it to go out of scope. That's crazy. That is not anything like I've used before. That's a totally new concept to just create this like arbitrary scope just to free up a variable. Huh. It kind of changes the designing principle. I might have to. Again, I don't know if I'll ever use this too often, but this is interesting. Rust enforces a similar rule for combining mutable and immutable references. All right. Okay, so why is this no problem? Oh, because it's not mutable. These are immutable, so you can have references. Mutable, so you can have reference. So it doesn't matter. You're just reading it. You're never going to write to it because it's not mutable. This one is a problem because, uh-oh, hold on. Which version of S is this one going to be reading? Or, sorry. Yeah, exactly. Yeah. Which version of S is R2 or R1 going to be reading? We don't know because it could be changed by R3, so that's a safety concern. Normally in languages, you just have to know, like, hey, this could happen, but it'll let you do it. Rust will tell you, what the heck are you doing? That is such a possible problem. This saves so much debugging time because I've come across race conditions before, and it's really just, it's really nice that the language can save you from that. All right, what else? Multiple immutable references are allowed because no one's reading. Yeah, that's what I said. No problem, no problem. So they're saying pass it into here, which should release. It should release the references. If I'm not mistaken, it should release. And then this is good. That's it. All right, dangling references. A dangling pointer, meaning a pointer that has been given to somebody else. And that other thing is preserving the pointer. Compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope because the reference to the data does. Will not go out of scope before the reference does. Oh, okay. If it's trying to reference that and for some reason that data gets cleared or dropped, you're good. It'll stop that. So let's see them do it. We have a function that should be returning its value to this variable. All right, dangle takes a reference, or no, returns a reference. The hello string, it returns that, which would come here. Okay, so it's holding this, but what if it gets changed? It won't let you do that. Expected named lifetime parameter. Because this should be an empty. As soon as you exit here, this would return. Well, S goes away. Hold on, now I'm getting a little bit confused here. How is this different from returning? They said you always return something. Oh, was that just the heap stuff? Oh, you always return the heap. That was for value. Never mind. Okay, this is for reference. So you're returning a reference. But the reference of the thing that you allocated in heap goes away. Because I think in that example with the value even, I don't think they were creating heap stuff in the function either. Yeah. Oh, wait, no, this one was. So this one was turning the value, not the reference though. The value gets put here and then you're good. But when you do the reference, hold on, where did that go? A little bit further down. Yeah, okay. When you do the reference, it is saying, hey, this value is no longer a known, like you can't have data here, it seems. So you're referring, yeah, as it says here, reference to nothing. And then it's talking about this lifetime idea. This function's return type contains a borrowed value. There is no value for it to be borrowed from. Consider using a static lifetime. So static would make it live across the scopes. I wonder if it's like in C where it's just to the entire scope of the RS file. If it is, I guess that would be pretty nice. That'd be pretty nice because it just pretty much is the same from C, I would think. But let's see, what do they have here? So dangle returns a reference to a string. Yep. S is a new string. Yep. We return a reference to the string, S, and then S goes out of the scope and is dropped. Its memory goes away. The reference is still passed out, which would be a pointer, but S, that memory is just deallocated. So S is created inside dangle. When the code of dangle is finished, S will be yeah, okay, this is just repeating the same thing. But their solution is this. Instead of passing the reference, they pass the value because the value will always pass it. And then you would just take that value into, what do they want it in? Into reference to nothing, which now is actually reference to something. Or not even a reference, it's just the entirety of it is moved to this. Interesting. Okay. Slices. Slices is a completely new concept. I'm guessing at least. You reference a continuous sequence of elements in a collection rather than the whole collection. Oh, so like a subset? Small programming problem. Write a function that takes a string of words. I just realized there's been no music playing this whole time. Maybe it's easier to listen to. I don't know. Either way, I've been listening to music this whole time. It's been helping me think. All right. Where were we? Okay. Write a function that takes a string of words separated by spaces and returns the first word in it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned. Okay, so you could dereference it? Oh wait, this is what it's saying. A string of words separated by spaces and return the first word. That's what you want. But if it doesn't find a space, then it's all one word. So how does this slices? Okay, you return a question mark. Is this dynamically sized return values? Is that what's going on? You have the string parameter. We don't take ownership. But what do we want to return? We want to return part of the string, but we don't have a way. So we could return the index of the end of the word indicated by a space. So if you do this, it's a function that takes a string, a reference of a string, you're borrowing it, and you're returning the size of something. You have bytes, which is guessing, you're seeing how many bytes the string is, how long. I'm surprised this isn't length, but I guess as bytes works. And then for this bytes, they are doing some function that I don't actually know. They call it down there. Okay, we'll get to it. And enumerating, I would imagine, is you count by one, perhaps. I see I, and I see a reference to some item. So if item value is 0, or not 0, a space, return I. What are you trying to do here? You're trying to see if there's no words, or if there's no spaces. Or, you'll see, the first word. I feel like you're trying to get to the end of the word, because then you would see a space, and then you return that. Otherwise, you return the length, which would be the size. This would be size as well. Huh. Returns the byte index in the string parameter. So you go through the string element, check whether a value is a space. We convert our string to an array of bytes using as bytes. Oh, okay. Character by character. That's what's going on here. So you take a string and you're counting through each character of that string until you get to the space. As soon as you get to the space, you return the index at which that space is. Otherwise, you return the length, which would mean that you are, what, on byte? Oh wait, no, return I. Yeah, I'm not quite sure. Let's see what they say. Create an iterator of the array using the iter method. It's an iterator. Oh, this stands for iterator. That's new to me. Iterators, yeah, exactly. All right, so iterator is a method. Turns each element into collection. And then enumerate wraps the result of the iterator and returns each element as part of a tuple instead. Wraps the results of the iterator? Okay, hold on. They should give an example here. The first element of the tuple returned from enumerator is the index. The second element is a reference to the element. The index and the reference, which they defined here. This is a tuple. This is a bit more convenient than calculating the index ourselves. So the tuple returned from enumerator is, so for blank in something. Okay, I should think back to what I've seen in Python or something, some other languages, for some variable inside of this thing. So each index is actually this. Okay, got it. Because the enumerate method returns a tuple, we can use a pattern to destructure the tuple. We'll be discussing patterns later. In the for loop, we specify a pattern that has I for the index in the tuple and a reference item for the single byte in the tuple. Because we get a reference to the element from itar and enumerate, we use the reference. You can also iterate with .a. Oh geez. Would .a? I didn't see it. Not the A. Oh, dot. You can enumerate with dot. Is that true? So you just do 4 dot dot? Inside the for loop, we search for the byte that represents the space. You're in Vim and tried going to the end of the line. I see, I see. Yep, I get that. Okay. So, hold on. Where the heck were we? So they're saying you're iterating I and the reference of item. So if the reference item is space, then return I, which is the index. Otherwise, return length. Length would be of the string. Just how many bytes are used. So I'm just confused why you'd be returning the length when you're looking for the first word. That's what I was thinking. Oh well. Where are we at? We have to find a way out of the index of the end of the first word in the string, but there's a problem. We're returning an unsigned size on its own, but it's only a meaningful number in the context of the reference string. In other words, because it's a separate value from string, there's no guarantee that it'll be still valid in the future. Okay, yeah. Consider the program here. So string, it's mutable. S is mutable, so it can actually be changed. You're passing it in the first word, which is this function up there. And because it's mutable, it could return. Actually, you're not actually returning anything. But why would you want to change anything in there? Yeah, in rest, you can iterate when you need a range for n in this. Okay, yeah. Yeah, I figured that's kind of the syntax that is allowed. Eventually got to that conclusion. I got a little bit thrown off by the tuple, not gonna lie. I'm not as used to seeing that just because I don't use Python as much, but that's nice to know you can just do a range like that. Thank you for the follow, Arn4VV. That's an interesting name. Arn4VV. Is that an acronym? Maybe some initials. Or maybe it's saying a word and I'm not saying it. Maybe RNAV. 4 equal A. 4 equal A. Am I missing the pun? I don't get it. Arnav. Okay. Oh, it's an A. Oh, I see now. Arnav. Okay. Sick. Thanks for the follow. Are you learning Rust too, Arnav? A few of us are all learning Rust for the first time ever. Okay. So, yeah, what was their point? What were they trying to do? So, they're saying the word will get the value 5. Okay, so hello world's passed. So hello world comes into here. Hello world. I guess they're trying to see how many spaces until you get to the space. Or sorry, how many indexes until you get to the space. So HELLO. And then you're at 5. If you start at 0, HELLO would be 4. If you indexed at 0, the 5th index would have to be the space. I would be iterated. So then you come down to here. Oh wait, no, return I would do 5. Okay. So you have 5. Cool. You done Rust for a work project, but it's mostly written by ChatGPT and audited by me. That's kind of how I was figuring out a lot of the C stuff, to be fair. Okay, so it's a little outdated, like it's using like a 2018, or not 2018, but like an older version of Rust in terms of like the syntax. That's good to know though, that its basic language stuff is doing all right. See, the best part is I wouldn't even know. I wouldn't even know if what it's showing me is outdated or not. Because, you know, first real time going into it. Okay, blue pill stuff. Say stream cut. Oh, yeah. Do you really think so? If you wrote it in Rust, it would have been easy. Oh, trust me. I saw that last bit of your sentence and I know exactly what you mean. The generated cube IDE stuff, it's hard to parse through. I really don't like the comments mostly. That's what really is annoying to me. But for me, the HAL stuff is just a bunch of structs that are passed around everywhere. And I mean, if you don't actually know the hardware, it doesn't really make it that much easier. So for some of the easier projects that I have, I just figured, you know what, I should just learn the registers on my own and just kind of do it that way. With Rust, I mean, it sounds like if the file is set up correctly, I can use the SVD generating thing to automatically set up some registers and maybe create a dependency thing where certain functions that trigger certain registers to turn on have a dependency on other pieces of hardware. And if I've read that part of whatever page I was reading correctly, that's like a huge lifesaver to me. I think that's like the most valuable thing out of all this, outside of like the other security stuff that they have built in. Like just having functions, I don't know, it's like if you're making an API and you need somebody to use your API, but they call things out of order, it's up to the developer to call it correctly. But if you force them to have to do certain things in order, like, I don't know, that just seems really good. Okay, not enough time to learn the hardware. Having to figure out interrupts, hardware clocks, and read that code. Yeah, exactly. Like, I think it's never a time where you just get to learn the hardware first. I feel like you just always get the generated stuff out, and you just kind of have to like parse through it alongside of the data sheet, and that's just what you're stuck to. There's not really another way, unless there's like an expert on your team or you have an expert that you're talking to. Like, from my experience at least, it's always just been, I gotta control click on all the references, all the functions, see where all the files are calling from to get some idea. And like, I don't know, I feel like it should be easier, but that's just my own experience. So, all right, what are we doing with this function again? Oh, right. We're trying to see how it actually works. So I wonder if you passed in an empty string to this. So if you pass an empty string, it should just return 0. It's my guess. So when would you ever enter length? Oh, you, wait. If you got to all the way by the end and there was no string, or there was no space, I mean, then the length of the string would be the index. Okay, I'm now seeing where the function's doing. Got it. Was the learning point here though that you needed to pass? Yeah, wait, what is the slice type? That's what we're trying to learn here. I was mostly just trying to figure out the function. I didn't even get to what the whole learning point was. Okay. But yeah, for RNav, we compiled the code on Rust. An example they had. So right now it has an example on it. I gotta turn on, just realized I need to turn on, I guess, Better TT Live or what? I see the ampersand quote, end quote. And I'm guessing this is, this comment is an emoji as well. Ugh, it looks like text emoji soup. That's an actual line? That's an actual line of code? Don't tell me that's regular syntax. Ampersand LT, ampersand hashtag 39, ampersand, or underscore ampersand G. Is that actually a real thing? If so, that is scary. That's an abomination, unfortunately. Okay, yeah. I'll come to this Stack Overflow. Let's see what this is. Okay. Oh, I see. Is it just these? Sorry for the flashbang, everybody. I know we went from dark screen to full bright white. Trying to figure out the ampersands. Is that what lifetime is? Oh, this denotes that it's a lifetime. Oh my gosh. This is usually written as this, where A is the name of the lifetime. Oh my gosh, I don't even... This just looks gross. Oh, generics, this is the template thing, huh? Yeah. This is a template with a lifetime, and then the space means, what did they say? The space means the compiler can infer the name type, so it doesn't need to make up a name. Oh, it's the type of it. It can infer the type. Okay, I guess that makes sense. It's a lifetime, whatever that means. I'm still not fully around that. But of unknown, like any type, really. Okay. Yeah, this is crazy. So Arnav, are you okay? So you used Rust a little bit. Are you learning to learn Rust some more? You trying to make more STM projects with Rust? Because I think there's a lot to explore there. That there's not too many like mainstream projects that have been designed on STM, or like maybe not products, but like projects that are built entirely out of Rust that have been like showed off around YouTube. Maybe there are, I could be wrong, but I feel like most of it, if it's going to be around, it's going to be HAL generated garbage out of the Cube IDE or Arduino, which both of those I'm trying to avoid as much as I can. I mostly want to stick with the Rust if I can, because I'm trying to better those skills and see what it can do. Okay. So the compiles without any errors. If we use Word after calling s.clear, because Word isn't connected to the state of s at all, Word still contains the value 5. Word should contain 5. Yeah, that makes sense. Because S is what gets dereferenced. Or not dereferenced, dumped. We could use a value 5 with the variable S to try to extract the first word out. But this would be a bug because the contents of S have changed since we saved 5 in Word. Yeah, so what would happen? Having to worry about the index in Word getting out of sync with the data in X is tedious and error prone. I agree. Managing these indices is even more brittle. If we write a second Word function, its signature would have to look like this. Oh geez, you returned 2 different things. Oh, you're returning a tuple use size. Now we started tracking a starting and ending index, and we have even more values that are calculated from data in a particular state, but aren't tied to that state at all. We now have 3 unrelated variables floating around that need to be kept in sync. Yeah, that's yikes. Luckily, Rust has a solution: string slices. You're not gonna touch STM anytime soon. You're learning. Can contribute to some Tari apps I use, and maybe write a SQLite extension in Rust. Oh, what is Tari? Hold on. What is Tari? I'm gonna look that up. Tari app. Oh, it's a framework. Is it a cross-platform framework for web apps? What is this? Optimized secure front-end implementation application. This is a front-end framework built on Rust, like React. It's like Electron, but using Rust. Oh, okay, thank you. Got it. Oof. Flashbang. Okay. That's cool though. I'm learning that like Rust is way more versatile, or at least, I mean, C was used in a lot of things to start out with, but it's definitely not the meta for desktop apps. Like, I would say the kernel is like the Linux kernel is like the main C thing that I hear about these days. It's pretty nice. I like to hear that. I love to hear that, actually. We like nice things. Alright, string slice. String hello. Alright. So they are... Oh. Man, I feel like if I just went to the bottom of this page and I saw the syntax, I would kind of almost instantly understand what's going on here. This is my prediction. You have string. You only want to pass the contents 0 through 5 to it, aka hello. Pass 6 through 11, aka world, to these. So, wow. But they want to show me this example, so I guess it's not that bad. All right, I got to learn about the for stuff. Hello is a reference to the portion of the string. We create slices using a range within the brackets, where starting index and ending index are the ends of the slice. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to the ending index minus the starting index. So in the case of let world equal to this, world would be a slice that contains a pointer from this to that. Cool. Slice syntax is pretty similar to Python. Yeah, that is nice. That's exactly what I was thinking of. Okay, so S, it's a string. And it gets hello, world all the way through. World has a pointer to this one element. No, yeah, the starting element of the string and then how long it is. Okay. Cool. So what are they going to do now? On a start at index 0, you can drop the value before the 2 periods in order to make that work. Okay, that's just like, all of these are just like Python. I think I can just kind of skip right through this. What would this last one do? Yeah, let's see. You can also drop both values to take the entire string. Okay, got it. So we want to return a slice. Yeah, I guess we can see. Oh, they're talking about where it's applied. I see now. So it returns a string. Oh, but they're not even calling it a slice or anything. They're just calling it an str. This signifies a string slice. Oh, so it's a legit keyword. Interesting. Okay, huh. So we wanted to return the address of all the spaces. It's a borrowed string slice. Okay, got it. Yeah, I'm gonna have to get used to using borrowed instead of reference. Where are we at here? Yeah, you're returning this range. I would be how long it gets to eventually. And you're returning the entire index. Every time item becomes this, wouldn't you... Oh, you're returning the entirety of it. So it's just the entire first word. I see now. And then this would return also the entire first word. Okay. And then if you want the second word, you do the same thing, just a little bit different. What are we at here? So we have the string getting passed into immutable S that's passed into here, which returns the word. You clear S, but word is still trying to access that. So this, yeah, I see this is an error because this is still holding on to what something got cleared. Okay, immutable borrow occurs here. Immutable borrow occurs here. This is immutable because you don't put mute in it. This mutates it. If we have an immutable reference to something, we cannot also take a mutable reference because clear needs to truncate the string. So this actually is returning it because we did this reference. I should have noted that. It's not dropping it or anything. It's letting the external thing borrow it. So word is borrowing the value that's inside here. And S is that original value. This is immutable. This is mutable. You just, most of the time when you just want text, you just use the reference, the borrowed string slice as the type. Okay. Okay. Good to know. And they're just explaining why that might be. Got it. So basically, I'm guessing they're just going to put mute in front of it. Needs to be after the call. Because clear needs to truncate the string, it needs to get the mutable reference. Println after the call to clear uses the reference in Word, so the mutable reference must still be active at that point. Rust disallows the mutable reference in clear and the mutable reference in Word from existing at the same time, and compilation fails. Not only has Rust made our APIs easier to use, but it has also eliminated an entire class of errors at compile time. Crazy. There is a use for string, but I'm not sure what all the differences are between string slice and string, but I think string is able to be built upon maybe. What can you still use string slice to call the additional slice, or sorry, the additional string functions? String is owned, yeah. That definitely seems to be the thing. String gets owned. String slice will only ever be a reference or borrowed. Unless you just can't mutate it. Maybe that's it. String literals as slices? Oh, they're talking about regular strings, I see. Double checked. String is dynamic heap. Oh yeah, that's very true too. Like vectors. Use it when you need to own or modify your string data. And string slice is a immutable sequence of bytes of a dynamic length somewhere in memory. Okay. So, oh, now I'm curious. This is our heap. This is our heap memory. We are pointing to this the whole time. When is this getting dereferenced? Oh, this is out. Okay, never mind. This is at the topmost level. I forgot about that. So never mind. It's always going to exist. S is going to exist here. It's going to exist here. It's going to exist here. When you clear it, it has an issue. So they need to do something new, which we'll see here probably. Or maybe not. Recall that we talked about string literals be stored in binary. Now that we know about slices, we can probably understand string literals. The type of S here is the string slice. It's a slice pointing to a specific point of the binary. This is also why string literals are immutable. Got it. So behind the scenes, when you are doing this step, the string slice, you're really just converting the heap into a static memory version of it, no? Oh wait, no, but it's still pointing. It's just pointing somewhere in memory. Huh. Because it was always heap. It was always heap when it was passed in. I guess that's why they're vague on purpose. They just said, where did they say? Somewhere with memory. The specific point of the binary. Yeah, that's the big part. Okay. Knowing that you can take slices leads us to one more improvement, and that's its signature. A more experienced Rustacean would write the signature shown in listing 4.9 because it allows us to use the same function on both string values and str values. Oh, really? Is that so? If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of the dereference cohesions. I suck at saying English words, I swear. That they define later. Define a function to take a string slice instead of a reference to a string makes our API more general and useful when losing any functionality. So hello world is set tr. You're gonna let my string be borrowed, but as a string slice of just the first 6 values. Actually 7 really, or unless 6 is not inclusive. Maybe that's exclusive, so maybe HELLO space. That could be it. And then you have word once. You're passing it again, but you're passing the entire thing. Why? What would happen here? Well, because you're passing it as a str. Oh wait, did they say change it to an str? Okay. What do they say? First word also works on reference to string s, which are equivalent to the whole slices of strings. This is making it immutable. This is immutable as well. What? How is it, I gotta think about this. It goes in. This would return the index, the word, as an str. Oh, okay. That's right. That was the key. It returns it as a slice. So the slice comes into here. The slice comes into here. They're both just memories, points and memory. Then when you get to here, you're pointing the heap back, but you're pointing the whole entire thing rather than just a string of it. Oh, okay, that's why. So if you called this twice in a row, they would have an issue, if I'm not mistaken. Let's see what they say. Word gets put into here. Okay, this would work as intended. Hello world is now a string literal. String literal is passed in. This would take the first word, that works. This would take the first word, that works. Because string literals are string slices already, this works too. Okay, this is fine. So it's just showing you all these would technically work. I feel like if you did this, well, maybe not, because you're returning the str again. You're not returning the full string. Yeah, never mind. Maybe it would work if you send it twice. String slices, as you might imagine, are specific to strings, but they're also general slice types too. Okay, so you can just work it on this, but you need to have the reference. Just as you might want to prefer part of the string, we might want to refer to part of an array. We do this with this. 1 through 5, you want just the first 3, you can do this, and then assert equal. Oh, that's a testing function, wow. Slice is equal to 2 and 3. Reference of 2 and 3. Well, this is gonna, not equal, I'm guessing. Oh wait, no, this is a macro because of the exclamation mark. This should fail. This slice has a type of signed 32, borrowed signed 32. It works the same way as string slices do by storing a reference to the first element and the length. You'll use this kind of slice all over everything. Yeah, this is more detailed. They talk about vectors later on. It's okay. Okay, that's a very dense part of the language, I would say. But that's important to know for sure. And I feel like when it comes to strings, that's like one of the core security flaws when it comes to languages. Like C, because it's just another array situation.